In this first example, we're going to take a look at the easiest possible Bessel function to work with, and we're going to have a Bessel equation to where the constant v is equal to 0. So in other words, we're going to solve this differential x squared y double prime plus xy prime plus x squared minus 0, or in this case just x squared y, is going to be equal to 0, and we're going to try to find the solution around the singular point x naught equals 0. We know that's going to be a regular singular point. In fact, if you wanted to verify that, you could divide the entire equation by x squared, and note that the root x naught equals 0 appears only once in any denominator. All right, so it's going to be absolutely a regular singular point. Just like we did, we're going to use the method of Frobenius because we have our singular point, and we're going to have these three definitions, and these are familiar ones. We saw these a couple times already in the previous section. So we have our y is equal to series n equals 0 to infinity c sub n x minus 0 to the n plus r, but we'll just say x n plus r. Successive derivatives are displayed there. And then we're also going to go ahead and just substitute those back into the original differential. All right, so I just did this ahead of time just to save us a minute or two of watching me fumble through this. All right. And then once we substitute, this is what we substitute into the second order differential, and we end up here. All right, so I'm assuming that's probably going to be good with everybody. Then we're going to do some algebra with this. All right, now just like we've done before, what we're going to do is we're going to multiply these coefficients of x and x squared into the series. And so we're going to get something pretty nice. So we're going to end up with series n equals 0 to infinity, c sub n, n plus r minus 1, and we're just going to add 2 to the exponent, which means that that negative 2 is going to cancel out, and we're left with n plus r, plus series n equals, in fact, I'm going to write this over top of the other one on purpose. So that's going to be plus series n equals 0 to infinity, c sub n, n plus r, and then we just add 1 in there to the exponent of the x, and that's going to be x to the n plus r. And we like that. And there should be an x up here, excuse me, I forgot to write the x. Right. And we like this because we already have x to the n plus r. It'd be really nice if the third term worked out that way, but alas, it will not. So we're going to have series n equals 0 to infinity, c sub n, x to the n plus r plus 2. It's not that big of a deal, but it would have been nice so that way we didn't have to do a lot more work. Okay, so there is an item of good news, and if you look really hard at the first two series, you'll notice that they both start at 0, so that's good. You'll notice that they both have Cn, they both have n plus r, and they both have x to the n plus r. So what does that make them? That makes them like series. And what we can do is we can add these series together. So I want you to notice that we have n plus r minus 1 of these series, and then we have one series. So what I'm going to do is I'm just going to add one series into this trinomial, and that's going to combine our like terms. So notice that we have n plus r minus 1 of the series, and we have 1 of the series. So if we add those together, we're going to get something really cool out of this. We're going to end up with series n equals 0 to infinity, c sub n, n plus r, times another n plus r, because the negative 1 and this one are going to cancel out when we combine the like terms, x to the n plus r, plus series n equals 0 to infinity, c sub n, x to the n plus r plus 2, right? And equals 0, and you're probably screaming at this point, well, you can probably write this first series as n plus r squared, and in fact that's what we are going to do. All right, so let's kind of simplify this and just rewrite this as n plus r squared, x to the n plus r. All right, so that's not too bad because the series are fairly compact at this point. All right. Now, just like we've done a number of times, we have to make sure that before we go on, that we have to make sure that our bases of x have the same exponentation. So we are going to have to use a substitution. We're probably very used to it by now. So n is going to be equal to k plus 2, which implies that n minus 2 is equal to k. And then also over here, n is going to be equal to k. All right? And these aren't too difficult to rewrite. So now we're going to rewrite the series. And the first series is now going to become series as k equals negative 2, because we have to subtract 2 from the lower bound. Infinity minus 2 is still infinity. C sub k plus 2. K plus r plus 2. And then squared. X to the k plus r plus 2. All right, so just added 2 in for, or k plus 2 in for all the n's. I just put k and r together. And then for the other series, that's going to be series k equals 0 to infinity. C sub k, x to the k plus r plus 2 equals 0. And happy day, now we can finally factor out that x plus r plus 2 once the index is the same. So what that means is from the first series, we are going to have to split off k equals negative 2 and negative 1. All right, so it's the same technique that we've seen a number of times. So let's split those off. So when k equals negative 2, that's going to give us c sub 0. We have negative 2 plus 2, and that's just going to cancel those out, so we're just left with r squared, and then we have x to the r power. When k is equal to negative 1, a little bit more complex, but not that big of a deal, we get c sub 1, r plus 1 squared, and then we get x to the r plus 1. And again, now we can go ahead and write our series, both with index of 0. So now we're going to get k equals 0 to infinity, c sub k plus 2, and we had k plus r plus 2 squared, x to the k plus r plus 2, and then finally we had one last series, series k equals 0 to infinity, c sub k, x to the k plus r plus 2 equals 0. All right. And now we finally get some good news because now we can factor the series out from the 2 that we have. We can also factor the x to the k plus r plus 2 power. All right, so by simplifying one last time, we're going to get c naught r squared x to the r plus c1 r plus 1 squared x to the r plus 1. And then when we factor out the series, k equals 0 to infinity, x to the k plus r plus 2. That is going to leave us with c sub k plus 2, k plus r plus 2 squared, and then plus c sub k. And that should be equal to 0. All right. So now we're at the point where we can go ahead and try to find a recurrence relation and then also set up a system. All right. Now, we already know one trivial solution is when x equals 0. And clearly, if x is equal to 0, x is equal to 0, x is equal to 0 right here, I mean, yeah, that makes it true, but that's very trivial. All right, we don't care about the trivial solution. We have different powers of x's. All right, so what we can say is that we have a system. We're going to have c naught r squared is equal to 0. And then we're going to have c1 r plus 1 squared is equal to 0. All right? And remember, on the right-hand side of this equation, we could write that there are 0 x to the r's plus 0 x to the r plus 1, similar to our undetermined coefficients method. So that's where all this is coming from. And then we also have the recurrence relation. We have ck plus 2, k plus r plus 2 square plus c sub k is going to be equal to 0. All right, so there's actually 3 equations in this system. All right, now we know that C naught can never be equal to 0. If it is equal to 0, then that's bad. Then we can't necessarily get a solution. All right. Remember, we get that indicial equation. All right. And what we're going to do is we're going to pick either C naught or C1 and try to solve it for R. And it's pretty clear that if C0 R square equals 0 and C naught cannot equal 0, that means that R square has to be equal to 0. Or we get the two roots, R1 equals R2 equals 0. All right? And what that means is that we can substitute 0 back in for K, or for R, excuse me, and then try to get our recurrence relation a little bit later. All right, that's going to give us one of the solutions. And we know that there's the other solutions that we need, but we just want one of these to get J naught. All right. Now, remember, we could also, and we're not going to do this, but I'm just going to illustrate that, we could say that C1 R plus 1 square is equal to 0. All right. And what this means that, remember, we just got that R was equal to 0, so this means that C1 has to be equal to 0. All right. And again, we just got that because C0 can never equal 0. All right, so if R equals 0, that means that C1, 0 plus 1 square is equal to 0, which implies that C1 has to be equal to 0. And we're going to hold on to that, all right, because that's going to be important. And so now what we can do is we can finally utilize the solution from the indicial equation and substitute it back into our recurrence relation. All right, and what do we get? Well, we're going to get that since R is equal to 0, all right, and it doesn't matter which R we're going to pick because they're both the same. But let's just say R equals 0. That means that C sub k plus 2 of k plus 2 squared plus C sub k is equal to 0. Or if we solve that for C sub k plus 2, what we're going to end up with is the opposite of C sub k divided by k plus 2 square. And that is our recurrence relation. And in the next video, what we're going to do is we're going to finish this off. We're going to use the method of iteration, and let's see if we can come up with a solution, or at least some sort of series representation for Bessel's J sub naught.